So last week we really got into a lot of theory regarding vector equations and matrix equations and kind of starting to put these things together in a way that didn't involve systems of equations. And then I ate my own words and ended last week's videos talking about these homogeneous and non-homogeneous systems and really trying to describe what a solution set to those systems of equations might look like and how the non-homogeneous version is actually very closely related to the solution to the homogeneous version and all that good stuff. And so I figured that, since a lot of you are STEM majors and many of you are probably interested in the actual applications of linear algebra, I figured I would start off with applications specifically of these systems of equations. So here we are again, we're back into another video talking about systems of equations. Hopefully this will be the last one in a while because next video I get to start talking about some of the really interesting ways that we get to use matrices that are not, something that you're all familiar with, which is very exciting. But for now, we're going to cover 3 different applications of systems of equations and ways that we can use matrices and matrix algebra to figure out some interesting information. So the very first one, this first application, is about how to determine equilibrium pricing in some sort of economy. So we are, taking some liberties with the simplicity of this example. And what you're looking at here is a small chart that basically says that there are 3 companies, coal, electric, and steel companies, and they all produce some sort of good. They provide some sort of good that is purchased by the other companies. And this is a closed economy, so we're not worried about there being other players or having unused product or something. We're starting with just a very, very simple example. And so how you might read something like this, let's say I were to read this column right here. What this basically says is that the steel company, right, the steel company right here, produces steel, and 60% of what they produce gets purchased by the coal company. So the coal company is purchasing 60% of their product. 20% of their product is going to the electric company, and then another 20% is going back to the steel company. And you might be wondering, what do you mean 20% is going back to the steel company? So they're buying their own product? Yes, yeah, that's how it works in an economy. The steel company probably needs the steel for their own manufacturing or for expansion or whatever it is. So it's not unheard of to have a company buy its own stuff. Similarly with the electric company, they have to reserve some of their own product for themselves because otherwise, without electricity, you can't really run the electricity factory. So the goal of this application is to figure out a set of equilibrium prices that make sure that no one company is price gouging or making a profit or something like that. We just want the perfect pricing scheme based on all of these kind of distributions of goods that is equal and fair to everybody. So what do I mean by that? Okay, so what that means is we are looking to set prices. We're looking to set some prices for these goods. So set some prices for these goods. And the way that we might do that is we might say that there's like a price for coal, there's a price for the electricity, and then there is a price for the steel product. And if we're talking about finding equilibrium pricing, okay, what that means is let's say we're talking about, what price, how much should I set the cost of steel to be, right? How much should I charge other people? Well, if we're talking about equilibrium means a balance, a perfect balance, right? We're not weighted one way or the other. So let's say we're talking about the price of steel. If we're talking about equilibrium, that means that whatever price that we set the steel at needs to kind of perfectly balance the distribution of the goods to the 3 of these companies. So what does that look like? That means that since I know that 60% of the goods right? 60%, or zero point 0.6 if you will, 60% of the steel is going to the coal company. The coal company is purchasing it at the coal company's price. So they're buying it at this particular price. And then the electric company is purchasing it at their own price. And then the steel company is buying back its own goods at their own price. Okay, and these prices are probably not the same because it's equilibrium. So we have something like this. And what we can do is we can do this for all three of them. So we could say, okay, well, if we're talking about balance, right, whatever my price that I'm going to set for my electricity needs to balance out, what's coming in as income on the other side, right? So if I do this, then I have, all right, the electricity company is giving 40% of their goods to the coal company. They are taking only 10% for themselves. And then 50% is getting consumed by the steel company, like so. And then last but not least, we have the coal prices. So the coal company doesn't take anything for themselves, but 60% of the coal is going to the electric company, and then the leftover 40% is getting used by the steel company. Okay. And so what we have here is a system of three equations, three variables, and we have this, in theory, like this kind of balance that we'd be looking for. And solving something like this, at this point, is fairly easy. What we can do is this is just a system of equations with three variables like we've been solving in the past. And so, I would probably set this up as a homogeneous system. So at this point, I'd probably go over here and I'd probably move all of these variables to one hand side of the equation and get that 0 is equal to 0.6 the coal price plus 0.2 the electricity price. And then if I subtract that to the other side, I'm going to have minus 0.8 of the steel price. Then I have 0 equals 0.4 of the coal price. I'm going to have minus 0.9 of the electricity price, and then plus 0.5 of the steel price. And then last but not least, we have 0 is equal to, now we're going to have minus 1 of the coal price, plus 0.6 of the electricity price, and then 40% of the steel price. And there you have it. This is just a setup for a system of equations. I'm not going to solve this. Solving it is not anything too rigorous. If you do solve it, or if you feel like pausing the video right now and checking it out, what you're going to get is you're going to get a solution vector. Like when you solve this, if you want, you could set it up as a solution vector where P consists of the coal price, the electricity price, and the steel price. But what you're actually going to find is you're going to solve this system, and you're going to get that your steel price is a free variable, and you're going to get a vector like this. You're going to solve this homogeneous system just like you did any other system last week, and you're going to get something like this. Now, how do we interpret this as a solution? Okay, well, visually, this is just like some infinitely long line in 3D space. But in terms of maybe the practical application of this, what this says is if you set a steel price, right? If the steel company sets a particular price, then the other companies need to set their price accordingly. Specifically, the coal company needs so if the steel company is selling their product at $10, right? If the steel company says, all right, it's $10 per whatever unit of steel, then the coal company needs to sell their price at 94% of that, or $9.40 per unit, and then the electricity company needs to sell their product at 85% of that rate, or $8.50 per unit of electricity, whatever it is that's being sold. And this would maintain a perfect balance. This would make sure that nothing gets out of sync. And largely this is how economies work. They do strive for this. They do strive for this balance. But what happens in economies is there's always some free variables, and those free variables tend to control the market. So if, for instance, the steel company decides to raise their prices because inflation, or the steel company, the goods for making steel is just really, really hard to source, or whatever it is, if that goes up, it immediately affects every other company in the economy, because they have to adjust their prices based on the price of steel. That's what this solution vector basically says. So this is a pretty interesting first example. You can imagine that the more complicated you make your economy, the more companies you have, the more things you want to consider. You can get as crazy as you want, but this is I think a good starting point as a first application of systems of equations. So the next application has to do with balancing chemical equations. So if you've taken a chemistry class before, you will be very familiar with this concept. And if you haven't, I will briefly kind of give you an introduction to what it means to balance a chemical equation. So, this molecule right here, this thing, this 3 carbon and 8 hydrogen atom looking molecule, that's propane. And O2, that's good old-fashioned oxygen. Now, what happens when you combine propane and oxygen in a little spark? You get a reaction. Heat comes out, right? Normally you get fire, heat, and then your byproducts is a little carbon dioxide and a little bit of moisture, a little bit of H2O, which is water. But something you might notice, right, is that even though, one thing that tends to happen a lot in chemistry is we observe that a reaction happens, right? We observe that if you take propane and you light it on fire and it combines with oxygen, that you get carbon dioxide and water left over. But if you're doing the math and you're doing some counting, you're noticing that, hey, there's 8 hydrogen atoms going into the left side of this equation, right? There's 8 of them. And how many are coming out on the right side? Well, there's only 2 coming out on the right side. And I don't know about you, I'm, okay at math. And last time I checked, 8 is not equal to 2. And so you might say, okay, well, that's weird. How about the oxygen? And the oxygen's even weirder. There's 2 oxygen going in, and somehow we're producing 3 oxygen on the way out. That can't work. Conservation of energy. You can't just randomly, you can't put in 2 oxygen molecules and all of a sudden they spawn a baby 3rd oxygen molecule. And so what we do, what's actually happening behind the scenes is, we say, okay, well, if 8 hydrogen are going in to this reaction, that means every time we burn and we take one of these molecules, which has 8 hydrogen atoms attached to it, maybe 4 of these H2O molecules have to come out. And you're like, okay, that makes sense, because that would mean that now there's 8 hydrogens coming out. But then you say, okay, that's cool, but we still have the problem where we have 2 oxygen going in, but now according to this, we have 2 oxygen coming out and another 4. Now we have 6. Now we're even more unbalanced. You say, oh, we have 6 oxygen going out. Okay, maybe we should have 3 oxygen on this side. And we're like, okay, we've checked off the hydrogen, we've checked off the oxygens, and then you're like, oh no, but by doing that, how many carbons are going into this equation? 3 carbons are going in. How many are coming out? Just 1. So you're like, oh, well, I'll solve the problem. I'll put a 3 in front of that. But putting a 3 in front of that throws off the number of oxygen. And then we have to go back and work with this. And it's kind of a repetitive cycle. And so what happens here is ideally when the dust settles, there is going to be some coefficient, some x1, some x2, some x3, and some x4 here, that basically indicate that in order for this reaction to happen, in order for it to be what's called a balanced chemical equation, we're going to need a certain amount of propane and a certain amount of oxygen, and it's going to give off a certain amount of carbon dioxide and a certain amount of water, right? And so it turns out that it's not just equal, it's not just 1-to-1, right? It's not just, oh, we just put in 1 propane molecule and 1 oxygen molecule, and we're going to get out 1 carbon dioxide and 1 water molecule. That's not how it works. Turns out that it's like baking a cake. If the recipe calls for 3 eggs, you don't just cook it with 1 egg. You would have to have 3 of these eggs in order to make the cake. So sometimes you need more than just 1 molecule to make the reaction happen, and that is where linear algebra comes into play. So this is actually really cool, because what we can do using linear algebra is I can describe this propane molecule right here. I can describe it using a vector. And what I'm going to do is I'm going to create a bunch of generic vectors. And these vectors, maybe I'll make it in green down here so we can kind of see what's going on. I'm going to put my carbon atoms in the first one. I'm going to put my hydrogen atoms in the second slot and the number of oxygen atoms in the third slot. So I can describe this, this propane molecule here by the vector 3, 8, 0. I could describe this oxygen molecule that we have here as 0, 0, 2. And then I can describe, it's basically that if I take x1 of the first one and I add it to x2 of the second one, in theory, what should happen? We should get x3 of this third one, and so we have 1 carbon, no hydrogen, and 2 oxygen in this one, and then we'll get an x4 of our remaining H2O molecule, and since there's no carbon, there's 2 hydrogen and 1 oxygen. This is the equation that we have. So what do we do with this? How do we solve this? It's the same exact thing if you want to think about it as a system of equations. You could set it up in such a way where I put everything onto one side. And so what we'll have is right now this is a vector equation. So we have x1, and I'm going to start using just one color now. So we're going to have 3, 8, 0 plus x2 times 0, 0, 2 minus x3 times 1, 0, 2, and then minus x4 times 0, 2, 1. And all of this should equal, if I put them on one side, just the 0 vector. And again, at this point, we have a vector equation, or again, you can think about it as a system of equations, but here, it actually may be more convenient to just notice that, we have a vector equation. I could put this negative sign inside of this vector. I can put this negative sign inside this vector here. And what we're basically going to create is the matrix equation, where we have 3, 8, 0, 0, 0, 2, negative 1, 0, negative 2, and then 0, negative 2, negative 1, with 0, 0, 0 here. And again, this stems, right? Remember that this system is equivalent to the matrix equation AX equals the 0 vector, where this x is basically our solution vector. It consists of our x1, x2, x3, and x4. And A, of course, consists of all of these individual column vectors like so. So this is just a kind of a follow-up of concepts from last week. And the idea, again, is that we can quickly solve this and hopefully get some sort of answer. So maybe for this one, I will solve it since I didn't solve the last one. So if I'm doing this one, let's see. The first thing I would do is I'm going to replace row 1 with 1/3 of row 1. And the reason I'm doing that is because I want to get a 1 up in this little first spot here. Again, you could have swapped the first 2 rows and turned the 8 into a 1, whatever makes you happy, but I'm just going to go ahead and start by doing this. So if I do this, let's see, we're going to get 1, 0, negative 1/3, 0, and then 0. My second row stayed the same, 8, 0, 0, negative 2, 0, and then 0, 2, negative 2, negative 1, 0. Okay, great. Let's see, next up, what am I going to try and do? So next up, I'm probably going to get rid of this 8, and I'm going to replace the second row. What am I going to replace it with? I'm probably going to take 8 of row 1 and then subtract row 2 from it. And so let's see, what is that going to give me? So my row 1 is staying the same, 1, 0, negative 1/3, 0, 0. My row 3 is staying the same, 0, 2, negative 2, negative 1, 0. But my row 2 now, okay, this is a 0. I multiplied 0 by 8, so it's still 0. Now, if I multiply this by 8, I get negative 8/3, and then I'm subtracting 0, so that's negative 8/3. And then lastly, I multiplied 0 by row 1, or 8 by row 1, which is 8 times 0. And then I subtracted row 2. So this is now a positive 2 and then a 0. Okay. So now let's see. My next pivot is actually here. So I'm going to swap row 2 and row 3 and then simultaneously, so I'm going to swap row 2 and row 3. And then what I'm going to do is I'm going to multiply that new row 2. I'm going to multiply that row 2 by 1/2. Okay, so let's see what we get here. So we have 1, 0, negative 1/3, 0, dash, 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 0. My last row is 0, 0, negative 8/3, 2, 0. And then my middle row is now 0, 1, negative 1, negative 1/2, and then 0. That's doing those operations. So I have 1s and 0s, so this is actually almost an RREF. The very last step, of course, is going to be to get our last pivot, which is right here, and to turn that into a 1, which I get by taking row 3 and then just dividing by negative 8/3, or you can think about it as multiplying by negative 3/8. So negative 3/8 times the existing row 3. And so if we haven't made any mistakes, any algebra mistakes, which, 50-50 chance we make algebra mistakes, we get 1/3, 0, dash, 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 0. We get 0, 1, negative 1, negative 1/2, 0, 0, 0. Okay, this is a 1. Now, if I do 2 times negative 3/8, that should leave me with a negative 6/8, which is a negative 3/4, and then that's a 0. And so the very, very last step, of course, is to turn these all into zeros via adding. That looks like a little bit of addition here. So my row 2, I'm just going to replace by adding row 3 to it. And then my row 1, I'm going to replace by taking, it looks like 1/3 of row 3 and adding it to row 1. So if I do that for the very last step, we get 1, 0, 0. My last row is all set, so that's 1, negative 3/4, and then 0, 0, 0. Then we have, okay, so this is 1, this is now a 0. And since I'm just adding those two, negative 1/2 minus 3/4 is the same thing as negative 2/4 minus 3/4, which is a negative 5/4. And then at the top, we have 1/3 times row 3 and adding is going to give me my 0. And then 1/3 times row 3. So 1/3 times this is going to give me negative 1/4. And I'm just adding it to that 0. So this is negative 1/4. So if we haven't made any mistakes at this point, what this tells us is that, remember that at this point, this is like our x1, this is our x2, this is our x3, and this is our x4. This is the equal sign and 0. And so I'm just going to jump one step and say that this gives us that x1 is equal to 1/4 x4. This gives us that x2 is equal to 5/4 of x4. And it gives us that x3 is equal to 3/4 of x4. And of course, at this point, this also means that x4 is a free variable because there's no restrictions here on what x4 can be. And so how does this make sense? Like, what do we pick for our answer? So I'm going to circle this and kind of bring it up to the top with us, back to where we were. Scroll up just a little bit, and there we go. Okay, so that little thing right there, remember that we're looking back at this this chemical equation that we have here at the start. What's our answer here? Well, it doesn't make sense to say pick x4, since x4 can be anything, right? Since x4 can be anything, we could say, okay, this is 1. Would 1 make sense as the answer? Well, that wouldn't make sense because how do you get 1/4, right? If I put a 1/4 here, right, because I let x4, if this x4 is 1, this basically says x1 is 1/4. What does it mean to have a fourth of a propane molecule? What does it mean to have 5/4 of an oxygen molecule? That doesn't make sense. And it turns out in chemistry that when you solve these equations, we need these coefficients here in the front to be whole numbers. We need our x1, x2, x3, and x4 to be whole numbers. So a good choice here for x4, since x4 could be anything, we can choose of our own free will that x4 would be equal to 4, for instance. And if we do that, if we let this be 4, that tells us we need one of the first molecule, because when I plug in 4 here, I'm going to get x1 is 1. If I plug in 4 here, I'm going to get x2 is 5. And if I plug in 4 here, we're going to get 3 here. And at this point, let's check our answers, right? We can run through this very quickly and run through. So this says we have 3 carbon atoms. This says we have 3 carbon atoms. Good. We checked. We have balance. If we look at all the oxygen atoms, we have 10 on the left side. I'm going to have 4 times the 1. So I have 4 here, and then I have 6 right here. So that's 10. So that balances. I have 8 hydrogen and 8 hydrogen. We've done it, right? We have achieved balance. Now, could you have picked another number for x4? Sure. Could you have picked 5? No, this wouldn't make any sense. You couldn't pick 5 because if you pick 5, we're going to get fractions for all of these coefficients. And again, that doesn't really make much sense to have a fraction of a molecule. We need whole numbers. But I could have picked, instead of 4, I could have said 8 of these molecules or 12 of these molecules or 16 or something like that. But we typically pick the smallest number that we need to make the reaction happen. And it's kind of like the idea of reducing fractions. You just kind of want to pick the lowest possible number to make this happen. So this is the second equation of using to creating systems of equations. And actually we kind of created vector equations here, but very closely related to systems of equations as well. And we're able to balance these out. So the last application of systems of equations is actually with something that hopefully none of you are super familiar with, which is network flow or traffic distribution. So I don't know if you've ever been driving on the road and you ever see like there's these 2 wires that kind of like cross a road, and then your car drives over it, right? That's your little car, and your car drives over it. And what these little wires do is they register the number of cars that go over, that are going down that street. And you'll notice that they're not on every single street because mathematically they don't need to be. It turns out that you can use linear algebra in such a way that you don't need to be recording all of every single street to measure every single car going over because, truth be told, we don't have that much equipment, we don't have that much time. It'd be kind of too tedious. So what you're looking at here is a collection of roads, and they all, traffic is traveling in various different directions. And some measurements have been taken and some amounts of traffic are missing. So for instance, if cars are coming here, it's registered that maybe on a daily basis, 400 cars are coming from this direction. And at this intersection, cars might turn this way, cars might keep going. Now they can't make a right turn, but then also coming into this intersection are another 100 cars that could also be making a turn or going straight. And so on and so forth. And at every intersection, things could happen. They could go straight, they can make a right turn here. Here, the cars could go left, they could go straight. So this is a very simple diagram. It kind of represents streets you might find in a city where there's a lot of one-way traffic and, there's not really bi-directional traffic. And the idea here is to, without having actually gone and done all the measurements for all of these roads here, is to mathematically come up with the amount of traffic going in every direction in this same particular day. And this is really useful because if I'm trying to figure out, where do I want to put my gas station, what corner do I want to put my gas station at, it's a good idea to know that, maybe there's a certain amount of traffic going this way, and maybe there's 150 cars going this way, and maybe there's 78 cars that end up going this way, and mathematically, because all of these intersections have to work together. We have inputs, outputs, we have to have balance. Right? We can't have more cars coming in and not enough cars coming out because then you get traffic jams and things like that. So we're assuming that because cars are coming out, cars are going in, cars are going in, cars are coming out, that we have flow in our traffic system. And so the question is again, well, how do you go about solving for these missing variables? And the very first thing you should do is count up how many variables you have. So since in this particular case we have 5 variables, we have 5 variables. Guess how many equations we should probably be coming up with to solve this? We need 5 equations. We need 5 linearly independent equations, it turns out, but you know, for simplicity's sake, we need 5 equations. Okay, and so the way that you come up with these equations is by reading this little traffic map and creating your own equations based on what you see from this map. So for instance, let's take a look at this first intersection, okay? In this first intersection, at intersection A here, what do we notice? We notice that there's 500 cars going in plus 300 cars going in. So there's 800 cars going in, and then there's X1 and X2 cars coming out. So one such equation that we know is true is that we have 800 cars going in, and that has to equal the amount of cars leaving that intersection. Has to. It's not possible. Cars are not mysteriously vanishing here like the Bermuda Triangle. It's not happening, right? So we have to have equality. So let's go to the next intersection over here. How many cars do we have coming in? Well, coming in, we have X2 and X4 of them. And how many going out? We have X3 and then another 300. So from this second intersection, we can create the equation. We have X2 going in plus X4 going in, and that should equal my X3 coming out plus 300. So if we do this for all the other ones, if we do this for the C intersection, it looks like we have 500 cars going in, and we have X4 plus X5 leaving. And then in the D intersection, we have X1 plus X5 going in, and we have 600 cars leaving. Now this, at this point, is how many equations? This is 4 equations. So you're like, okay, well, what are we missing? Well, the very last one is, it makes the most sense, but it's also the hardest to think about if you've never been shown it. The last equation comes from the total amount going in. The total in has to equal the total amount of cars going out from our enclosed system. And we view this as a closed off system because this is the parts of the streets we're analyzing. So let's look at the entire system and look at all the cars going in. So all the ones going in, and then all of the cars going out. And we can create one more equation from that where we get that there's 500, right? There's 500 plus 300 in, that's 800, plus another 100, that's 900. This is 1,300 in. And that has to equal the fact that there's 600 going out here, there's 300 going out here, and X3 going out there. So there's 900 plus X3 going out. And at this point, we have done enough, right? At this point, we have done enough. We have 5 equations made from this system that model this traffic flow, right? These are all the different relations that we get here. And so this we can go ahead and set up. I'm going to rewrite all of these to be of the same form where we have all the variables on one side and all of the numbers on the other side. So I'm going to write this as x1 plus x2 is equal to 800. This next one I'm going to write as x2 minus x3 plus x4 is equal to 300. This one's going to be x4 plus x5 is equal to 500. We have x1 plus x5 is equal to 600. And last but not least, we have x3 is equal to, 400? 400. Okay, great. And so from this, even though we already have x3, to solve this using matrices, we can set up, this is a non-homogeneous system, but we can set up a non-homogeneous augmented matrix here where we have 800, 300, 500, 600, and 400. And even though we already know what x3 is, I'm just going to do this to put it in. And remember that our first column is going to be representative of x1. This is x2. This is x3. This is x4. The last one is x5. So if we pop everything in, we're going to have 1 x1 and 1 x2 and then 0, 0, 0. We're going to have 0x1, 1x2, minus 1x3, 1x4, then 0x5. We're going to have 0, 0, 0, 1x4, 1x5. We have 1x1, 0, 0, 0, 1x5, then 0, 0, 1, 0, 0 here. And now we have a 5 by 5 augmented matrix that just basically consists of a bunch of ones and zeros. So we RREF this and we get our solution. We RREF and that gives, to our solution. And that'll tell us the distribution of traffic based on the measurements that we took, and got these numbers at all these intersections. So that's going to do it for this video. It's 3 pretty interesting examples. You can read about them in the textbook if you feel like you need a little bit more concrete. They are all from the textbook. But that should do it for these examples. Hopefully you thought that they were interesting. And if you really like systems of equations and applications, then I'm very sorry to report that we are going to move on to some more theoretical and abstract mathematics. I'm very excited about it, so head on to the next video to start learning about a little bit more on linear independence, but we're going to start talking about these things called transformations.